Assalamu alaikum everyone. So lecture number 5, and today we will be discussing about wireless transmission media. So let's start. So this is an overview. First we will talk about wireless transmission media and the methods involved. Then there we will take some examples: terrestrial microwave, satellite microwave, broadcast radio, infrared, and we will also compare them. And then we will talk about different wireless propagation modes, and finally we will be talking about multiplexing, that is time division multiplexing, frequency division multiplexing, and wavelength division multiplexing. So let's start. So first, wireless transmission. As we know, this is an unguided media. As a result, the transmission and reception are being done with the help of antenna. So we can have two different types of transmission when we talk about the unguided media, that is wireless media. First is directional, and the second one is omnidirectional. In directional, we will be focusing on a single point, right? So the transmission antenna is focused on a particular point, or it throws the beam on a certain point. So in order to accomplish that, the transmitter and transmitting and the receiving antenna, they should be aligned properly in order to have those focused beams for transmission and reception as well. For the omnidirectional, the signal spreads out in all directions, right? So if we throw a pebble within a water, the waves that spread out can be a very good example of omnidirectional communication or omnidirectional transmission. So as a result, the antennas which are within the range, right, they will be able to receive the signals if they have the capability. So these are the examples. We have terrestrial microwave, satellite microwave, broadcast radio, and infrared. So let's talk about terrestrial microwave. So this type of system or technology or communication is being used for long distance communication. It uses the radio spectrum that starts from 2 gigahertz and it ends up at 40 gigahertz. So we need a parabolic dish transmitter, and it should be mounted on the top of some roof or some mountain, right? So it is actually used by private networks as well as by common carriers. So we need line of sight communication between the source and the destination, right? So the antenna should be aligned as we discussed. So we also take into account the curvature of the earth, because this is a long haul communication, right? So the curvature of the earth should be taken into account, right? So let me draw here. So you know that we have the curvature of earth like this, and if I have an antenna over here and an antenna over here, so I should be taking into account the curvature, right? So that is the curvature of the earth, right? So you can see that if I have to draw a straight line between those two antennas, right? So there will be an obstacle, that is the earth. So we have to take into account the curvature of the Earth. So in order to, so let's draw here, right? So I'm not able to draw it properly, so you can draw yourself, right? So let's have an antenna over here, right? And antenna over here. So now I can draw a straight line between these 2 points, right? So you can see that now the communication will be achieved. And here are some of the applications of satellite microwave, right? So television, right? Long distance telephone transmission and business network, private business network. So as mentioned, we need line of sight communication. Antennas has to be aligned, so this can be regarded as the one of the disadvantage, because in order to build towers we have to spend resources, right? And if you need repeaters, then you can imagine that the cost will rise. So there can be interference, right? For example, if we have a scenario like this, right? The two antennas that are being aligned, and there is an object passing by. For example, there can be an aeroplane, or there can be a bird that is passing, or sometimes heavy rain, it can also produce an interference. So this is also one of the disadvantage of this type of communication, right? So here we have the satellite microwave applications, so it should come after this slide. So you can consider that this has to come after this slide, right? And this is this slide represents disadvantages of overall microwave transmission. So for satellite microwave transmission, we need a microwave relay station in space, right? And the job of that relay station is to relay signals over long distances, right? So let me show you that how, for example, we need to transmit from this part of the Earth to this part of the Earth, right? So you can see that if I want to transmit from here to here, so this is not possible. So what I can do, I can have a satellite over here, right? And so this is the transmitter and this is the receiver. So what can be done over here in this scenario, the transmitter will transmit signal, right? And this satellite, it will repeat the signal and will again transmit here, right? So we need a satellite that is actually relaying the signal between. So from here to here, this will be the transmitter now, and here we have the receiving side, and again the satellite will be repeating, right? So we can achieve, you can see that the geographic access will be much higher in this way. So we need geostationary satellites because our Earth is moving as well as it is revolving, right? So it remains above the equator at a height of 22300 miles geosynchronous orbit. So as I have mentioned, Earth is revolving and moving, So this satellite also has to synchronize itself with this rotation and movement in a circular path, that is almost a circular path. So Earth stations, in case of satellite microwave, communicate by sending signals to this satellite. So we need two different frequencies, one for uplink and the other for the downlink, right, to the satellite on an uplink. The satellite then repeats those signals, right, that is the downlink, and for a downlink we should specify a frequency. Right, so here is the scenario. So as I have mentioned, so this is the distance. You can imagine the axis, right? So here we have the uplink station and here we have the downlink. So this is the transmitter, and here you have receiver, and this is satellite having transponders. So we have a transmission from here, right? So you can see the line of sight communication, and then we have the satellite is repeating the signal and transmitting it again, and here we have the receiver side downlink. We have different applications. You can see we can have dish antenna where the television services are distributed or broadcasting, and all the dish antennas they are receiving at the same time. So there should be a transmitter, right? So the scenario should be like this. Here we have satellite, and over the earth we have different antennas. Right? So the data is being broadcasted. Okay. Direct broadcast satellite. Okay. So we have some of the bands that are reserved for satellite transmission, C-band, and for C-band we have 4 to 6 gigahertz, 4 gigahertz for downlink, and 6 gigahertz for uplink. And then Ku band, 12 downlink and 14 uplink, and these are gigahertz. As mentioned, there can be interference. Rain can be one of the reasons for interference. Then we have Ka band. This is for Ku band, 19 gigahertz for downlink and 29 gigahertz for uplink. So we need specific equipment in order to use those different bands for satellite transmission. So as we know, if we look at the electromagnetic spectrum allocation, so microwave transmission, it covers actually a very large portion of the spectrum, and the range start from 2 gigahertz and it ends up at 40 gigahertz. So as we have studied the rule, the higher the frequency used, the higher should be the data rate or the higher potential bandwidth, right? So therefore we can have higher data rate. So here we have the performance chart, right? So this is the band and bandwidth, effective bandwidth, and the data rate, right? So So here again, microwave transmission characteristics. So as mentioned, the main one of the impairment is the attenuation. So we can have an expression for the loss, right? So L is the loss, 10 log 4 pi d over lambda whole square, and that loss is mentioned in dBs. So where d is the distance and a is actually the wavelength. So lambda should be the wavelength, right? So let me correct. Lambda is the wavelength. So you can see that from this expression that the loss varies at the scale of the distance, right? So because for a particular frequency we have a fixed bandwidth, so you can say that this has to be a constant. 10 is already constant, 4 is also constant, pi is also constant, and we already have the scale, right? So loss actually varies as a scale of the distance, right? So if we have greater distance, right, so we will be having, there are chances of greater loss. So as opposed to twisted pair and coaxial cable, where the loss actually varies exponentially with distance, right? So this is the difference. So as a result, so as mentioned that loss in case of twisted pair and coaxial cable, it is varying exponentially with distance. So we need repeaters or amplifiers at a greater distance as opposed to in microwave transmission, as opposed to transmission when we are using twisted pair or coaxial cable. So you can see 10 to 100 kilometer. So this is same attenuation is increased with rainfall, and there is a certain frequency, 10 gigahertz. So above this frequency, the effect of interference, the interference due to rainfall, it can really affect the communication. So we can also have another sort of interference, that is the transmission areas overlapping. So hence the frequency allocation should be regulated. So here we have a comparison of fiber and satellite transmission. So as the frequency range of fiber and the satellite, they are close, right, and the data transmission rate, it's also comparable, so that's why we have a comparison over here. So we have mentioned different characteristics, optical fiber and then satellite. So bandwidth, theoretical limit of 1 terahertz. So currently we can support 1 to 10 gigahertz. This is the actual bandwidth. So for satellite communication, transponder has a bandwidth of 36 to 72 megahertz. So immunity to interference. So as we have transmission by using light waves in case of optical fiber, so there are no charges on photons that are actually carrying the data. So there is no EMI, electromagnetic interference, right? So they are more immune to interference. So for satellite communication, there can be interference from different sources, right? So, and we have already discussed those interference. First, there can be interference due to rain above a particular frequency, and there can be also an interference due to irregular frequency allocation. So the frequency allocation should be followed by certain rules. Then security. So it's very difficult to tap without detection, right? So if you are tapping, so you will be only getting photons, right? So you need a full-fledged system, and you need the transmission, need to know the transmission mechanism, communication mechanism between sender and transmitter, and then you are able to detect what's being transmitted, or you can say you will be able to grab the data, otherwise you will be only getting the photons. So for satellite communication, right, so as we have satellites in space, so the signals should be encrypted for security, right? So you can realize the importance of encryption when we talk about satellite communication, right? And then multi-point capability. So primarily for optical fiber, we have point-to-point medium, right? So we started from one point and we end up at the other point. That is point-to-point. So at the moment we only have point-to-point, right? In case we are using optical fiber. And for satellite communication, we can have point to multi-point, right? So we can have the example of dish antenna, where the satellite is broadcasting and it is being received on the earth by many dish receivers. And then flexibility. So it's difficult to reconfigure the change. So for satellite, they are easily configurable. So connectivity to customer site. So as I have mentioned, now the service providers, they are being provided optical fiber connectivity for the local loop, or you can say for the last mile, and you can imagine the data speed that can be achieved by using the optical fiber. So for the satellite communication, we need to install antenna and align it properly in order to achieve that for the local loop. So here is the radio communication, and radio is omnidirectional and microwave is directional. So the frequencies, they start from 3 kilohertz and they go up to 300 gigahertz. That is the range for radio communication. So mobile telephony occupies several frequency bands just under 1 gigahertz, right? So you can imagine the quad band frequency that is being used in case of cellular communication and for GSM, right? And here we have the infrared. So in case of infrared, non-coherent infrared light is modulated, and then it's being transmitted, it's being used for transmitter and receiver. So transceivers must be within the line of sight. So the best example is the remote control for a TV, for dish antenna, for any device within a room. So, but that is not a transmitter, right? So because the communication is one direction, right? So you can say this is an example of a simplex, one directional communication, right? So here we have satellite versus terrestrial. So as we know, satellite communication works when there is a line of sight, right, from the communication satellites. So same is the case for terrestrial microwave communication. And as far as antennas are concerned, we need parabolic antennas for both satellite and terrestrial communication. So overall, satellite and terrestrial, they actually are using almost the same technology. The only difference is the distance between the sender and the receiver, right? So one provide more distance and the other provide a bit less distance between sender and receiver, or support. You can say the distance between sender and receiver supported by satellite is somewhat different from terrestrial. So there is only one main difference, that for terrestrial we have point to point, right? And for satellite the path becomes, we transmit from Earth, then the signal reaches at the satellite that is in space, and then the satellite repeat via the transponder and then transmit it to another antenna, that is the receiving antenna, onto the Earth. So the path becomes Earth, space, Earth. So that is one of the main difference between satellite and terrestrial communication. So here we have the comparison between radio and microwave. So the main difference between radio and microwave is that in case of radio we have omnidirectional communication, and for microwave we have the focused communication. So we need antennas to be aligned, but for radio communication we don't need any alignment, right? So if you are within the reach, you can receive the signal if your device have the capability. And one of the example is our cellular phone. If we are within the reach and or you can say that the carrier have the service in that area, then there is no requirement for the alignment of antenna, so we can receive the service whether we are in the line of sight or not, right? So it covers FM radio and UHF, ultra high frequency, and VHF, very high frequency, that are being used for television. Then we have a packet radio that uses a ground-based antenna to link multiple sites in a data transmission network, right? Teletext services that are also in the radio, and then we have cellular radio that I have mentioned. Okay, so here we have infrared versus microwave. So one of the key difference between infrared and microwave, that the infrared, it cannot penetrate, but the microwave, it can penetrate into the obstacle, right? So security and interference problem encountered in microwave systems are not there, right? So as we know that in case of infrared, we modulate non-coherent light, and that we use that sort of modulated non-coherent light in order to transmit and receive, and this communication is confined within the room or maybe within the building, so there is no requirement for the frequency allocation, right? So it's actually being used, is using non-licensing frequency band. So if there are chances of high-fi electromagnetic interference, so it's better to use the infrared communication as opposed to microwave communication, because then we can have greater amount of EMI or interference, and there are some of the advantages regarding the weather in case of infrared communication. So here we have the whole story. So we have mentioned here different frequency bands, the ranges of frequencies, and then the wavelength range, and the propagation characteristics that are being used for those different frequency bands and their uses, right? So you can see we have mentioned extremely low frequency, and the frequency range is from 30 to 300 hertz, and the wavelength is 10,000 to 1,000 kilometer, and the propagation methodology used is ground wave, right? And for voice frequency range 300 to 3,000 hertz, and the wavelength is 1,000 to 100 kilometer ground wave, right? And used by the telephone system for analog subscriber lines, PSTN lines. Then very low frequency 3 to 30 kilohertz, and the frequency range is 3 to 30 kilohertz, wavelength range 100 to 10 kilometer, right? And the propagation use, that is ground wave, right? So you can have an idea. So here we have the infrared frequency range 300 gigahertz to 400 terahertz, and you can see the frequency is higher and the wavelength is very short, 1 millimeter to 770 nanometer. Line of sight communication, right? So you need to align the receiving and the transmitting antenna, so you can imagine the alignment required for in case of remote control device. Infrared, LANs, consumer electronic applications, right? So here we have VHF, UHF, SHF, super high frequency and extremely high frequency, right? And here we have the visible light, right? So these are the different wireless propagation mechanisms, right? So first we will start from the ground wave. So you can see that the ground wave communication or propagation, it follows the contour of the earth, right? So here we have the transmitting antenna, and on the other side we have the receiving antenna, and you can see the path adopted by this wave propagation mechanism, that is the ground wave propagation, right? So the frequencies required in order to have this sort of wave propagation mechanism, they should be up to 2 megahertz. So one of the best example that we can quote is our AM radio, amplitude modulated radio communication, that actually is following ground wave propagation mechanism. In fact, for ground wave propagation, the wave is confined between the surface of the earth here, that is the surface of the earth, and the ionosphere, right? So here in space over here, we have a layer that is ionospheric layer, right? So the ground wave actually propagate between the surface of the earth and that ionosphere. So here we have the Skywave, right? So you can see that this is the transmitting antenna, and here we have the receiving antenna, right? And this is the contour of the earth, and this is the ionospheric layer, right? So shown here as a solid line, right? So you can see the propagation, mode of propagation of Skywave, right? So antenna is transmitting, so the wave travels, right? So there is a reflection back and forth between the ionosphere and the contour of the earth, and that wave is received over here at the receiving antenna, right? So the utilization of this propagation mechanism is in amateur radio, CB radio, and international broadcasts, right? So you can see a signal from earth-based antenna is reflected from the ionized layer of the upper atmosphere back and forth, right? So you can see that we have number of hops bouncing back and for back and forth between ionosphere and the earth's surface, right? So here you can have the actual Skywave propagation, right? So you can see these are the Skywave propagating around the contour of the earth. So this sort of communication is useful when I want to transmit a signal from this part of the earth that is not directly in the line of sight, right? So if you look at the contour of the earth, so if you want to have a line of sight communication, right? So you have to have an antenna at a much greater height, right? So you can say that even maybe a satellite is more feasible if you want to build that much amount of height using a tower, right? And the antenna should be mounted on that tower, right? So let me right. So for example, you want to have transmission, right? So this is the height, and you want, so you can see that there cannot be direct line of sight communication between those two antennas, right? So in that case, you need to have raised the antenna to much greater height, right? And then we can have the satellite communication, line of sight communication, right? So maybe it's better to use the satellite, right? So in that case, we can use Skywave propagation mechanism, and then maybe we can have transmitting and receiving antennas over there, and you can see that signal can be received in this way, right? So here we have line of sight, right? Wireless propagation, line of sight. So you can see this is the contour of the earth, and here we have the transmitting antenna and receiving antenna, right? Line of sight. So it actually works above 30 megahertz. So the reason for this line of sight communication, that the ground and the skywave propagation, they cannot operate above 30 megahertz. So the communication must be line of sight. So let's talk about refraction, right? So when the electromagnetic wave, it enters from one medium to another medium, it bends from its original path. That is called the refraction. So obviously when that kind of electromagnetic wave, it enters from one medium to another medium, its speeds also varies, right? So see, as mentioned, velocity of electromagnetic wave is a function of the density of the medium. So as a result, when any electromagnetic wave or light, which is also a kind of electromagnetic radiation, it enters from one medium to another medium. So as the density of one medium is different as compared to the density of the other medium where the wave is entering, so it bends from its original path, and speed is also varied, right? So that's why we take that whenever electromagnetic wave passes through the free space, its speed is almost comparable to the speed of light. So we can define the index of refraction, that is the sine of incident wave divided by sine of refraction angle, incident angle and the refraction angle. So it varies with wavelength. So gradual bending, right? So density of atmosphere decreases with height, right? So the atmosphere becomes less and less denser as we go higher and higher, right? So result in bending of radio waves towards the earth. So that's why you can see the bending over here. So the density of atmosphere decreases as we goes higher and higher. So as a result, the bending of radio waves towards earth occurs, right? So here we will discuss some of the impairments when we talk about wireless line of sight communication. So we can come across free space loss, right? So as the signal travels distance, right? So it can come across free space loss, right? So this can be the case when we are actually transmitting a signal from satellite over to the earth, right? So there can be free space loss, right? Then we can also have atmospheric absorption, right? And then multipath interference and refraction, right? So this can also be one of the impairment for line of sight communication transmission. So here you can see the example of multipath interference, right? So you can see that we have line of sight communication over here, right? And you can see this signal is being received by this antenna straight away, but here we have the interference, right? So the best example is GSM, right? So it can cause errors and affect the quality of communication, right? The errors are due to inter-symbol interference, right? Equalizers are used in order to accommodate, right, or correct the ISI, inter-symbol interference. So we have certain techniques like orthogonal frequency division modulation, and rack receivers may be used in order to overcome this multipath interference, right? So let's talk about multiplexing, right? So here we have n inputs, right? And we have n outputs. And the there is only one link if you take this as a transmitter and this is the receiver. So one link between transmitter and receiver. So you can take the example that within the city we have different inputs, let's say n inputs, and this data has to be transmitted over a longer distance to another city, right? And then it has to be distributed, right, into n outputs, right? So this actually is the phenomena of multiplexing is all about. You multiplex n inputs and transmit all the data of that is from n input lines over to a single line in order to transmit that data, for example, for longer distances, that is from one city to another city, right? Then over the other side you have to distribute this data to n lines, right? So this is a very generic explanation of multiplexing, but in order to, in the context of our subject, right, so we have the case when the capacity of the transmission medium exceeds the capacity required for the transmission of a single signal, right? So we need to make an efficient use of this transmission capability, transmission power, right? So in order to do that, we carry multiple signals onto a single medium, right, as shown here, and this is referred as multiplexing. So there are a few reasons. As you know that every communication facility, it costs, right? So cost per kbps, kilobits per second, declines with an increase in the data rate, right? And the cost of transmission and receiving equipment declines with the increase of data rate, right? So everything is tied up with the data rate. Most individual data communication devices require relatively modest data rate support, right? So these are some of the reasons for the use of multiplexing. So we have different techniques: frequency division multiplexing and then time division multiplexing. So it takes the advantage of the fact that the useful bandwidth of the medium exceeds the required bandwidth of a given signal, right? And here we have time slot allocation for each. So you can see that if I have predefined time slot for all the n inputs, right, and then on the receiver side the same has to be done. It means the sender and the receiver has to be synchronized when we are multiplexing. That achievable bit rate of the medium exceeds the required data rate of a digital signal, right? So here we have FDM for frequency division multiplexing, right? So you can see as we know that each signal requires a certain bandwidth, right, centered at a carrier frequency, right? So we have frequency here F1, F2, F3, F4, F5, F6. So these are the channels, different channels. So in order to avoid interference, we have the guard bands in between those different frequency channels. So as an example, that we if we talk about voice communication, right? So voice bandwidth is, or spectrum is, from 300 to 3400 Hertz. So we need a bandwidth of 4 kilohertz in order to carry the voice signal, right? So 6 different channels are shown here. So each signal requires a certain bandwidth centered on its carrier frequency, right? but we have not shown over here the guard bands. Right, so we have the whole frequency band over here, and we have chunked down those different frequency bands. So we have chunked down the whole frequency band into a smaller frequency channels and named them F1, F2, F3, and then we can use those different channels in order to communicate individual carriers. So this is the division in frequency, and here we have time slot, right? So this is the time axis, and each channel is allocated a predefined amount of time, right? So channel 1, channel 2, channel 3, right? Time slots are pre-assigned and fixed, right? So you can see the division of each channel is assigned a predefined time location, right? So that's why I mentioned that we should have a synchronization. If we talk about if this is allocated a predefined amount of time slot, and then second, third, and so on and so forth, so these has to be synced. So if we consider a switch over here, when the switch is connected over here on the receiving side, at the same time that switch has to be connected over there, right, in order to have the synchronization. So this is the TDM, right? So here we have shown the whole story, right? So here frequency and time, you can see separation of whole spectrum into smaller frequency bands. A channel gets a certain band of spectrum for the whole time, right? So you can see different colors are showing different channels, and then we should have some guard band in between. So this is the time division. So here we have the division in frequency band, you can see, and here we have this division in time. Each frequency is allocated, or each input is allocated a certain amount of time slot. And then we are performing both, right? So you can see that if I cut those different slots, right, I place F frequency division and time division one onto the other, and then I cut, right? So you can see that this is the time and frequency multiplex. Right, so here we are using the combination of both. Channel gets a certain frequency band for a certain amount of time, right? So for a certain amount of time it is getting a certain frequency band, right? So the best example is GSM. So here code multiplex, right? So that I will not go into detail, we will discuss. And here we have multiplexing in more than 2 dimensions, that is frequency and time. So you can see space, time, frequency, and code, right? So you can see frequency, space, time, and code, right? So we have we can have multiplexing in 4 different dimensions, multiple use of shared medium, right? We can also have wavelength division multiplexing. This is the case, the application or the example that can be quoted in case of wavelength WDM is multimode optical fiber transmission, right? So we can transmit light of different frequencies, right, onto optical fiber by using this wavelength division multiplexing, right? So that's all for today's lecture. So today we have discussed about wireless transmission, and we talked about different wireless propagation modes. Then we talk about the multiplexing techniques we are using, and we discussed frequency division multiplexing, time division multiplexing, and wavelength division multiplexing. So that's all. अपना ख्याल रखिएगा, मेरी तरफ से अल्लाह हाफ़िज़, अस्सलाम वालेकुम.